Good afternoon, everyone. We are Group 3 and we are here to present the plan that we have designed for Aerospace Design 2. Thank you so much for being with us here today. This class is a senior capstone design project where we get to show off the last 4 years of undergraduate engineering that we have experienced at UF. To talk you through how today is going to go, we're going to recap some of the mission requirements, objectives and goals, design processes, and analyses that we did. For those who were here with us last time, you might remember some of those. And then we're going to catch you up to date on what has happened since then, including the manufacturing and test flights.
So for the mission requirements, the first and foremost thing that we needed to do was build an RC plane. More specifically, it had to fit within these specifications. And then with these specifications, we then had to make sure that the plane could take off of this runway, complete this course with doing 3 laps, and then eventually landing without taking any structural damage and being able to do it safely and effectively.
So for our objectives, we want to meet the given mission requirements, of course, but also we wanted to design an aircraft with surveillance capabilities. The main reason is that for this is just because we saw that this is a growing need in both military and commercial applications. So we thought we would try to do it with our senior design project. And then we'd also want to design aircraft modularity for a couple of reasons. One being that one of the resources we use for manufacturing is a 3D printer, and you can only 3D print so much at one time. So doing it in small sections is easiest and quickest. And then also if we wanted to make any repairs or design improvements, we can do that easily with different sections. And then before we get into the nitty gritty, we have our full CAD model visual for you guys. This is just so you get the whole picture before we start going into how each component was designed and manufactured. And then for our design process, we started with phase 1, where we got the basic initial estimations. These we kind of used for different deciding factors throughout the design process. And then we designed the wing as well. And then for phase 2, we tackled the fuselage, propulsion system, landing gear, and a structural analysis of all those components. And then for phase 3, we did a tail design and a full stability analysis of everything.
So our plane is designed around surveillance and reconnaissance. So what our whole design process started around was the wing itself. We wanted to create a lightweight structure that had enough integrity for the mission that we were trying to carry, and also design self-similar parts that reduce the amount of design time, manufacturing time, as well as assembly time. For this, we used lightweight PLA for our 3D printed core, around which we did carbon fiber layups. And we also use carbon fiber spars, which are used to support the wings and hold them within the fuselage. For the airfoil selection, we wanted to select around the cruise characteristics of the plane. The NACA 4412 gave us the best performance in terms of our lift, our drag, and our efficiency in our given flight regime. For the flight geometry, we started with hand calculations and later moved on to the software XFLR5. We use iterative design to create a wingspan of 1.68 meters, a taper ratio of approximately 0.8 to increase our efficiency, a root chord of 0.216 meters, which is roughly 8.5 inches. And finally, we aligned it along the quarter chord, and this is what gave us the optimum design. For the internal geometry, our main features, we start off with the rib. These have been hollowed out for supports. Instead of circles, we went with the ellipses, and those allow us to run cables throughout it. We have 3 spars. These are good for carrying the loads within the wing and also give the wing enough structural support for us to do the layup around it. Finally, we have a full support for the spars. We use this at first for a different reason, but it was very useful for our manufacturing process, and it also reduced the bearing stress when the carbon fiber spars are acting on the wings. For the winglets, we use lightweight PLA to minimize the weight, especially important given the fact that it is out on the edges. We minimize the dihedral because we did not want to increase the bending stress on the wing itself. And finally, we were able to make these winglets removable by the use of shaft collars that are inserted into different rods on the wing. For aileron sizing, we focus on aircraft of similar size and similar flight characteristics. So we went with 40% of the half span as shown here, 25% of the root chord, and we also use the torsion rod design. So the entirety of the aileron is going around a metal rod essentially that is placed within the wing. For the design itself, we optimize the clearance to reduce the aerodynamic instability that can arise in this section. We also use a carbon fiber link. This carries the torsional load within the aileron and was also used as a shear connector. And finally, we placed the control horn at almost exactly the hinge line. This gave us a good amount of command over our control surfaces while minimizing the torque needed for our aileron servos.
So for our fuselage, our overarching goals were to optimize the strength and weight of it, make sure it's structurally sound, and importantly, make sure that it's modular and easy to assemble and work with. The way we did this was with 3D printing. So we used regular PLA. We had an internal structure comprised of frames and longerons throughout the fuselage, and the wing and tail connection sites were particularly reinforced because that's where most of the forces were going through. The sections of the fuselage were split into 6 individual 8-inch sections, and the main reason for this was the maximum print height of our 3D printers supported about 8 inches, and access hatches were placed on each of the sections for, like I said, easy assembly and working with the components once it's assembled.
And then here's a detailed CAD of our fuselage where you can see the access hatches and the different sections. The total length was 4 feet, including the tail. This number came from a textbook reference we used in our design process that used a fixed wingspan number to calculate that 4 feet that we got. And then for the shape, is a rounded square for most of it, and it tapers off into a more circular shape at the end. The square shape is just to have a flat surface at the bottom for all the attachments we would do, like the landing gear and the camera gimbal we'll talk about in the future. And then also the circular shape is to have the motor mount securely attached to it as well.
So these images show more of the internal structure of the fuselage. We'll start with looking at the frames that run down the length of the fuselage that are each 8 inches apart. And these frames serve as the places where the sections are split. So the way they're manufactured is at the midplane of each of the frames, the part is split off and 3D printed. And the holes in the frames allow for both weight savings and to remove the support structures that are associated with the 3D printing. Between the frames are 4 equally spaced longerons at the corners, and these serve to transfer most of the bending and torsional forces away from the relatively weak skin and to the frames. Special tension was placed on the wing with an extra frame on the leading edge and tubes that run through the indents to support the wing bending load, and the wings are kind of inset into the fuselage to provide some mechanical engagement for the bending stresses. Also, the front and rear landing gear brackets where they're attached are reinforced on the inside by being attached to the frames. And you can see the access hatches, which are cut out here, have tabs on each of them so that they rest on the top 2 longerons with Velcro, and they're easily removable and secure.
Our propulsion system hasn't changed since our midterm evaluation, if you were here for that. So we have a battery, a motor, a propeller, and an electronic speed controller. Our battery was chosen to have sufficient flight time for a drone plane, and this proved well. For our 5.5-minute flight, we used about 60% of the battery.
Similarly, the rear landing gear did not change much from our midterm presentation. We kept with the tricycle formation in order to make sure that we would have sufficient clearance for our pusher prop. The rear landing gear is a curved carbon fiber leaf spring, and we kept with the rubber wheels, even though they are a bit heavier, and that ended up paying off later, as you will see. A bit more on the actual design of the rear landing gear. The wheelbase and track are 2 very significant numbers. The wheelbase was 16 and the track 18 inches. The nose to wheel angle was 45 degrees, which is greater than the minimum recommended angle of 40. And the tip back angle was calculated to be 16.2 degrees. This tip back angle means that when our plane is coming in for landing or taking off, that we can have an angle of attack of about 16.2 degrees and still have clearance for our prop. Another really important angle is the overturn angle, which is really significant when it comes to taxiing the plane and the turn radius that the plane has. This angle was calculated to be 59.86 degrees. It's pretty close to the 63 recommended maximum. However, it was not an issue for our plane. Another thing to note is that the weight distribution between the nose gears ended up putting about 22% of the weight on the nose gear. Although the optimum range is typically 8 to 15% of that weight on the nose gear, the reason that it ended up being a little bit more on the nose gear is because we wanted to make sure that that nose gear was very stable and secure, so it was built into a bulkhead of the fuselage.
So moving on to the nose landing gear, starting with the nose wheel, we purchased a single nose wheel along with an aluminum rod attached to it and an internal damping spring to dampen out some of the landing forces. And then we attached that to our fuselage using a hollow carbon fiber spar and then a steel rod glued into it with about 1.5 inches of steel exposed to set screw onto our landing gear. And then this was all laterally supported by a lateral support bracket with a small truss structure printed out of PLA into the fuselage section that our landing gear was attached to. And then lastly, for the steering system, we used a 9-gram servo with a PLA and elbow bracket steel linkage system, as well as a strike plate fastened on with some standoffs. I'll show a better picture of that here so you can see the PLA linkage as well as the steel elbow joint that's glued into the carbon fiber rod. Other than that, both links on the PLA are free to rotate and the rod is obviously free to rotate as well. And
for our tail, we decided on a V-tail configuration. This had a few benefits over doing a conventional tail, such as having fewer surfaces to manufacture. Similarly, there was less interference drag from the surfaces going into our push prop, so there was more clean air going to the propeller. And once we decided on this configuration, we were able to get the final dimensions as you see here, using a NACA 0009 airfoil with a 15-inch span and a 6-inch cord. And then on the plane, it has a 30-degree dihedral angle and then a taper of 0.8.
For our design, actually, I'll skip one more forward. Our V-tail connection slot was a key part of our assembly. To emphasize, one of the objectives was modularity, and we wanted to be able to connect the fuselage at this joint, and then also the airfoils for the V-tails were connected in the slots with carbon fiber spar holes. In the rear, we had a mount for the motor where we would mount our motor, and we will see that implementation later. This airfoil is what the stabilator will actually attach to these holes here in the side. And if you look under, we have the servo mounts, which we were able to mount the arms of the servo directly into the hinge line for the ruddervator. And as you can see, we designed it with most efficient weight considerations. We had a spar printed along the airfoil and openings to allow for very efficient weight considerations. And for our ruddervator, we were able to attach the servo arm directly into the ruddervator for very compact and ease of movement in the V-tail.
next I'll be introducing the stability analysis that we did for our aircraft. So the first thing that we needed to consider in terms of how stable we wanted our aircraft to be was most importantly the center of gravity. So for the center of gravity, basically we wanted to be in front of the aerodynamic center of the airplane, which is indicated by this red dot here, which we calculated. And anything that is after that would basically cause the plane to be unstable, and then anything in front of it would make it stable. So the more that we would place it further forward, theoretically, the more stable that the plane would be. So with this in mind, we'd use something called static margin in order to calculate how far forward we wanted our center of gravity to be. We chose a percentage of 15% because most of the planes that we looked at with historical data ended up having 20% for those that were very stable, for example, like the Cessna, and then more planes that were less stable that were designed for more maneuverability, like fighter jets, ended up having something closer to 5%. So we chose something a little bit in between because we wanted a little bit of maneuverability, but we also wanted to have the good stability for our plane's design choices in mind when we're taking shots and pictures of different things with its drone purposes. So using this static margin equation, which non-dimensionalizes the distance, we calculated it to be approximately between a third to half chord, which is very close to where we ended up using it for the actual flight. Then, for our actual stability analysis, we calculated the pitch, yaw, and roll moments using XFLR, which is a simulation software that we use to do different iterative designs where we could change the wing length, the chord length, the taper ratio, all these different things, which was very helpful for us when we were trying to make decisions on which small differences between planes would actually be beneficial and be the most optimal to fly for our given parameters. And then once we kind of had those values set and saw which one would perform best, especially after we had designed the wing and the V-tail with the specific airfoils, we were able to confirm with the hand calculations that we did in MATLAB. So that was also very helpful because if we ever did need to make a change down the road, all it required was changing a specific variable that we had set in MATLAB for example, wingspan, so that we can then just run the code again and it gives us all of our new numbers and eigenvalues and everything to make sure that it's still stable.
And you know, as you can see here, we have our roll, pitch, and yaw moment coefficients, and we were actually able to successfully confirm all of those values using our hand calculations per the Goodmanson book and all of the equations in there, that our aircraft is stable and that the XFLR simulation is valid. So we did compare each of these values to some other historical aircraft, and they are all well within the range of aircraft flying in our flight regime. The only important thing to note from these variables is that these roll moment coefficients actually are a little bit on the low side in magnitude when compared to other aircraft in our flight regime, but that is purely due to us having a V-tail, and our values are very similar to some other common V-tail aircraft. And then moving on to our dynamic stability analysis, we plotted the state space variables for each of the longitudinal modes, specifically the two dominant ones in the phugoid mode and the dominant ones in the short period mode. In the phugoid mode, our two dominant states are airspeed and pitch angle, while in short period, the two dominating modes are angle of attack and pitch rate. As expected in the phugoid mode, it's characterized by a long time to damping, a long response, and then low damping, while the short period mode is characterized by high damping and a short response. And lastly, we can move on to the lateral directional modes. These, since they are multi-directional modes, it's kind of hard to characterize with, you know, a single set of plots. So we figured it was better to take some animations we were able to produce from XFLR5. First, for the Dutch roll animation, you can see our aircraft's response in terms of Dutch roll. And then moving on to roll subsidence, you can see both our stable modes coming back to trim conditions. And lastly, we have the spiral convergence. This is not as exciting of a video to show. It's more important just to note that the eigenvalue is positive and that we are on the stable side of the spiral convergence. And onto the structural analysis.
Now that we had built a plane that could actually fly, we had to make it not break during flight. We had a mixture of analysis during which we focused on the most important aspects of our plane. We were able to verify these all with hand calculations. The first one that we conducted was for the wing. For a more conservative approach, we first started placing 1/2 of the weight of the plane at the tip of the wing. This is only considering half the span of the wing. Using the values that we found for the strength of lightweight PLA and using this cross-sectional area, which is the most representative along the length of the wing, we estimated a factor of safety of 5. This gave us a good amount of comfort when operating in different turns, and we found that we were operating for within a margin of safety of 6. This gives us good security that our wings are structurally sufficient to fly within our flight regimes. We're not pulling any acrobatics, and we have a lot of play and give with these values. We were also concerned about the actual properties of lightweight PLA when we started the manufacturing process and how well it would withstand, as we will see later, for example, a touch on the runway or a roll and during landing. So we conducted our testing, and as the picture shows, some of our main concerns were proven correct. So the rib is very weak compared to the rest of the material, since usually the rib would actually be constructed of a stronger material. There was also a high amount of delamination occurring between the skin and the rib. This is due to the direction in which it is printed. There was a lot of skin integrity that was lost when we actually performed the destructive test, and this created ripples in the skin. And finally, it was very vulnerable to penetration from foreign objects. So here we have a tree branch, and then once it actually lost the structural integrity, it started cracking far easier, and those wings would no longer be airworthy in the case of a strike for the landing gear.
So onto the landing gear structural analysis, we kind of took the approach here as more of a research-based approach and then aimed to support it with some strong assumptions and some hand calculations. So from our research, we were able to gather that the FAA has a defined hard landing as hitting the runway at 3.05 meters per second. For our aircraft, that works out to about 4 Gs. And then from there, we kind of used our weight estimate distribution between the front and rear gear to assign how much force of that landing would be put on either gear. So from our calculations, as Marley said earlier, the range for the percentage of the load applied to the front gear is anywhere from 8% up to 15%. We kind of chose a safe number around 10% for the low end, and the high end was what we actually had, which was this 22%. We aimed to actually put both gears under the biggest possible load they might experience within our range. So obviously the front gear would take the full 22%, while the rear gear was going to take 90% associated with, the low end of the front gear range. And then we aim to simplify this process by approximating both landing gears as cantilever beams, with the front being a rod and the rear gear being a square cross-section beam or a rectangular cross-section beam. And then from this, we were able to gather some results using our stress and buckling equations. We found out that the aircraft actually wouldn't buckle anywhere before the stress would overwhelm the landing gear. So we didn't include any of those results in the calculations. But from the stress experienced, both bending and normal, we were able to gather a margin of safety for the front gear of 6.5 with a maximum deflection of 3 millimeters. And then for the rear gear, we were able to gather a margin of safety of 25.6 with a maximum deflection of the designed 25 millimeters or 1 inch.
As Ryan was discussing for that landing gear structural analysis, it did come back to tie into our original design, which was using the deflection and moment of inertia equations to calculate how thick their landing gear would need to be. So this height here is that height that is being measured there. Based on the assumption of a 4G landing, we wanted to have this is at the very bottom where the landing gear is at its skinniest. Therefore, it would need to be slightly thicker at 1 inch versus at 2 inches at the top. The theoretical height would be 7.5 millimeters. In actuality, due to difficulty with perfecting that carbon fiber thickness during manufacturing, it actually came out to be 8.17. All 3 different points, when it was 1 inch, half inch, or 1.5 inches, excuse me, and 2 inches, we were all sufficiently over what it needed to be, meaning that we were above the range of strength that we needed for the structural analysis of the landing gear.
And now to talk about our manufacturing process, just breaking that down. For starting off the wing, we 3D printed the wing with lightweight PLA, as for the people that are here can see on the table. And here is another visual though. And with these sections, we glued them after post-processing them and sanding them down. We glued them together to make it one complete piece. And from there, took it to Solar Park and did a carbon fiber layup, just 1 layer that epoxied it and let that cure for the weekend, and did some post-processing of that as well. And here is the final product of the wings. This is also with the ailerons and the servo motors attached to it as well.
As stated earlier, our fuselage was 3D printed with PLA, And the modularity of it allowed us to have rapid prototyping where we were able to adjust the design quickly as we needed. This came in handy for our first test flight where our front landing gear support was actually attached externally. And for the second one, we incorporated the design to be built within the 3D print of the fuselage. And additionally, would like to say thank you to Tom Singer and Dr. Ting for the suggestion of moving the fasteners between the fuselage sections closer to the longeron for some of those pieces. And lastly, the access hatches, as stated earlier, we do have 6 of them attached with Velcro, and these proved to be very helpful in manufacturing and assembly, especially in between test flights where we were able to fix things or check things when we needed.
And for the renovator, within the VTEL, our assembly or design process was to 3D print and PLA 2 sections and then attach them with a spar in the middle and then glue the middle section. And that was the design process for our stabilator. With the stabilator attached on the right, you can see the servo arm was directly attached into the stabilator, and it was connected via a carbon fiber hinge. And that allowed freedom of movement along the axis. And because the VTEL's airfoils were so thin because of the triple actually 9 profile, we wanted to directly attach it without having to mount the servo outside for a linkage system. And that was our approach for this design. If you can see on the implementation of our VTEL connection slots, the airfoils are connected on each side, and we have our our motor mounted directly in the rear with the 4 screws. And that worked out pretty well for us. We also designed it so there was ventilation in case of overheating to make sure the motor was always cool. And you can see also on the right image, we have another view of the connections of the VTEL and the propeller attached.
For our rear landing gear manufacturing, we started with a 3D printed PLA base. Then we wrapped that PLA base with 3 layers of carbon fiber. For the first layer, we angled the fibers at 45 degrees. Then for the next 2 layers, we angled them at 90 degrees. And then following the carbon fiber layers, we did 1 layer of fiberglass. And then we cured everything with epoxy resin. And we used this mold to hold the shape of everything onto the base. And once everything was cured, we post-processed the landing gear by sanding and finishing the edges and drilling the holes where the tires would attach.
Another part of our rear landing gear manufacturing process is really zoomed in on this picture here. The bracket that holds our rear landing gear in place, you can't quite see underneath it because it is fast in place, but there are 2 rubber O-rings around the landing gear that allow for flexion at the top of the fuselage. However, there are also little notches in that bracket that the O-rings slide into that prevent the landing gear from having any torsion in this direction.
And then onto the manufacturing of the front landing gear. Here is the landing gear with the strike plate installed. You can kind of see how it prevents the spar from going up through the fuselage during landing. And then here is actually the print with the lateral structural bracket printed into the fuselage. I know previously we mentioned we kind of had it on the outside, just glued on for our first test flight, but we were able to get it in there for the subsequent test flights. And then, you know, the set screws are located right here for fastening that steel rod onto the bottom landing gear.
Next, I'm going to walk you guys through our test flights. We had 2 different days of flying with 3 attempts on the first day and 2 on the second. This next video will show you our first attempt. As you can see, we go down the runway and unfortunately do not take off, and we run back into the bushes a little bit. All right. So the result of that first attempt was the aircraft did not take off, sadly. However, we did not have any damage anywhere to our plane. We had 0 structural damage. The rear and nose landing gear did very, very well in the off-roading. We determined that the cause of this failure was actually that the center of gravity was slightly too far forward. So we moved the center of gravity back to the 1/3 chord. And additionally, another change that we made was that we increased the range of motion for the ruddervators by increasing the gain.
So after that, we took to the skies again, and here's the video of that. And as you can see, we had a successful takeoff. Some twitchiness there on the climb, mostly due to very high roll rates for the ailerons. But after that, we were able to get it under control, and the flight was very stable. And this will show a little bit of that flight. Now here's our landing. So landing itself, pretty successful, but as you can see, after the landing, it's continued to roll off the runway, hit some very bumpy terrain, and kind of tumbled over itself and broke apart at one of the fuselage joints. So like I said, successful flight. The fuselage did get damaged a little bit because it kind of hit that bumpy terrain and did a little barrel roll there. We were able to super glue these sections back together and fly again very shortly. Here's some more pictures of the damage there. You can see that the extent of the damage was that the fasteners sheared through the PLA. One of the fixes we implemented for this later was getting some larger diameter washers to spread that force out a little higher or to a greater area. Here's some more pictures of the damage.
So for all our friends and structures that are asking yourselves, with such a high margin of safety, why did you decide to go for the carbon fiber on the skin? As we mentioned, one of our concerns was the damage that the plane could sustain, not during a very severe crash where the entirety of the plane nosedived onto the ground, as there is very little we can do about that, but about these little nicks, twists, and landings that may occur. As you can see here, the plane was basically on its wing as it hit that divot, and the wings were able to survive that due to the skin thickness. The winglets that we had mounted on at the time had a good amount of damage. However, because of the geometry, we were able to take those up. And you can see on this image here that because of the high amount of area that we provided for the carbon fiber spar that we're using to hold the wing in place, it was enough to take the bearing stress of the impact itself. And the pictures that you see here, both of these pictures represent the wings that we were able to use in subsequent test flights. They were still very much airworthy afterwards.
So here's our flight after that, once we patched it together. Once again, takes off, flies pretty nicely this time. So show a little bit of that flight. And the landing, well, almost landing. So as you can see, our plane did crash on landing there on this flight attempt. What happened was there was a wind gust that kind of kicked out right at the last moment on landing, and I was unable to recover the plane at that point. The plane dropped about 5 feet onto the runway, kind of on its side, and the fuselage section where the rear landing gear were attached was damaged. After that, we kind of decided that we weren't going to patch it or try to fix it at the field, and we we're going to go back to the lab and reprint it. Again, harping on our modularity, it was very easy for us to fix our plane. We just had to reprint the 2 sections, and we were able to fly again in a few days. And we have some more pictures of the damage here. Most of that force kind of went up right through the rear landing gear, and it broke the 3D printed PLA of the fuselage.
So there were a few things that we specifically wanted to do from the first day that we tested to the next day that we went out. The first one was to reprint any of the damaged parts that we needed to after that crash. The most important ones being some of those fuselage parts, as well as those winglets that we had. And then the second objective that we had was to also incorporate some of the equipment that we had not yet installed on the plane. So when we went out for the first time, we just wanted to make sure that the design itself was stable, that it flew, that we could actually be successful in those attempts, which we to some extent were. And now we went back to the lab to basically reprint the nose cone so we could put in that FPV camera in the front, as well as install a few more things that would be helpful for the actual things that we wanted to do for the aircraft and its applications.
So following these design changes, we went back to test flight again, and this is the first attempt on that second day. So as you can see, it's running down the runway, and once again, it does not take off. Yes, it goes into the grass. This time it did not sustain any damage from running off the runway. But the reason that it did not take off this time was because after the design changes and the implementation of the new electronics, our center of gravity was a little too far forward again. So we made some changes by moving it to the 1/3 chord, by removing some weight at the nose. And then,
Yep, just like first day, we kind of made some CG changes out on the field and we were able to fly again. And this is the video of our successful test flight after that. Let's take it off again. We have the FPV camera footage in that top left corner. And this will show a little bit of the flight. Yeah, it's not the most pleasant sound.
We'll also jump to a couple of the more important parts of the clip. Let's see if I can get there. Right around here. The end? Okay. There was a couple clips in here that we wanted to show that had the drone.
Only like 3 minutes is good.
This one?
No, the next one's right there. Yeah. Yeah, this was a shot that we had that was a little bit closer with the drone that we had.
We had one of our group members, roommates up there with a DJI quadcopter filming our flight. So that's where we got this footage from.
If anyone would like to see it more at the end, we will go back to it, but we're gonna jump to the landing.
buy one for the class.
Yeah. Here's our landing from that day. We had a slight crosswind on the runway, but we were able to bring it home in one piece. Yeah. There's our test flight.
and then this is some of the data that we got from that successful test flight that we were able to read. So overall, we used 3,000 milliamp hours on our battery, which was able to do 5,000 milliamp hours, so about 60% of the battery usage. And then we flew for a total of 5.5 minutes and with a max altitude of 150 meters. So moving on to our future applications of what we could do with this.
So yeah, as for the future upgrades we plan on incorporating to our design in this project, we have a camera and gimbal that Diego is about to go grab and show off real quick. That we can attach a GoPro to and have some in-air footage to live up to the surveillance goal of this aircraft. Not sure, hopefully you guys can see it. I'll give a close view here.
So we have this arrived today and we have a very fast mounting process to exemplify how it is going to go into the fuselage. This is one of the spare sections that we had done trial printing on. So you can see there are dampers here to prevent the rolling, and then the camera itself is supported by 2 brushless motors. And that is one of the things that we aim to do before the end of the semester, once again.
And yeah, with this camera, we'll be able to capture some footage, capture some additional data, and then, I mean, lastly, the long-term goal of this project is to get some autonomous flight capabilities in terms of landing and even taking off.
Thank you guys so much.
Thank you.
Great job. So really great. I was talking later that oh.
Any other questions?
I was gonna see, how do I check this? Well, if anyone would like to speak, I believe we should be able to hear you. If you want, please feel free to unmute and ask your questions.
Yep, sure guys, this is Tom Singer. Congratulations. Looks like a successful project, and it's always good to see these come together. Thinking back to my own senior design project, it went a lot better than mine did, so good work. let's see, on the structures on slide 17.
Yep.
So I see you've got like a little mini rib coming through the bump in where the wing sits. Where did that come from in the design?
So originally the wing was actually more forward so that it sat between these two bulkheads or frames up here. But when we were doing the stability stuff, we realized that we had to move the wing a few inches backwards. And we still wanted some kind of frame support at both ends, at the both leading and trailing edge of the wing. So we just decided to add one additional smaller frame there to strengthen that.
Okay. Yeah, good. I mean, I like seeing that. That's kind of your load path to the rest of your structure from you know, the loads between your wing and your fuselage. So that's nice structural design. I like that. On slide 35, more structure stuff. This is the wing analysis. So we did the analysis with half the weight of the airplane at the tip of the wing. What load case does that represent? And I understand that, you know, that's a conservative place to analyze a 1G load, but are you designing the wing for a 1G load here?
So that is one of the reasons why our design factor of safety was 5, since those were approximate weight loads that we found for banking maneuvers. So as you said, yeah, that's that 1/2 weight would be for our cruise. And with the use of the FPV camera and the gyro that was mounted on the plane, we went back and we were able to see that we were pulling up more of 3.6 Gs.
Yep.
So it is quite a bit for a turn. However, it was still below our factor of safety. This is already a conservative estimate, and it doesn't include the carbon fiber. And we were operating within a greater margin of safety for cruise conditions.
Okay. Yeah. So I would say, in general, the structural analysis ought to consider something other than just a straight and level cruise, right? So, I mean, it's one thing to say, yeah, we've got a factor of safety on our, you know, straight and level cruise, but if you're telling me the plane is capable of pulling 3.5 Gs, that's a design load that I would look at, right? And if you want to say, you know, we'll put 3.5 times half the weight of the plane at the tip of the wing and show good for that, that's a conservative way to do the analysis, and I'm okay with that. But definitely, you know, consider what your load cases should be. And then when you're telling me that you have a factor of safety of 5, are you telling me that you're designing to a factor of safety of 5? Or are you telling me that your structure has 5 times the capability that it needs?
That was the design factor of safety. In terms of the loads that we were actually pulling during cruise, it would be a margin of safety of 6.
Okay, so what you're saying is if you apply a 5G load, so that you're telling me your factor of safety on your 1G load that you would apply to that is 5, right? So 5G load, half of 5 times the weight at the tip of the wing, and then you show a margin of safety of 6 on that loading condition.
Sorry, I don't think it either cut out or I don't think I understand your question fully.
All right, so the design condition, right? The limit load would be a 1G load case, so half the weight of the plane, and you're assuming that's concentrated at the tip, right? And then you say we need to design to hold that load case times a factor of safety of 5, right? Like our design factor of safety is 5, so whatever load we expect to see on the plane, multiply that by 5 and show good for that,
Yep.
right? And then you're saying that in that analysis, with that factor of safety, you showed a margin of safety of 6.
Right. The formula that we had seen required the formula that we use for margin of safety in this analysis required us a set of factor of safety first. That is why that's why it is slightly higher for the same load case. So the formula that we used was required us to set a factor of safety first.
Yeah, good. I mean, that's what you should do. That might have come from me. So, yeah,
Yeah.
again, assuming this was your design load case, right? Then you're telling me that you can hold 5 times that, but you can also, the margin of safety tells me that you can increase your load by a factor of 600% and still show good at your required factor of safety, right? So essentially what you're telling me is you have like 30, you can carry 30 times your limit load here, which is substantial. You know, again, I realize that wasn't actually the right load case to consider, but if you're applying a big factor of safety and then finding a big margin of safety on top of that, that's like, yeah, that should be an optimization flag, right? Or a flag to like consider a more realistic load case. So,
Yeah.
let's see.
Okay.
All right. So on the I think on the landing gear analysis on slide 37. Yeah. Okay. So you've got a hard landing defined as like a velocity, like a vertical velocity at touchdown, right? And that comes from the FAA. So how does that convert into a G loading then?
Yeah, so how I calculated that was essentially just treated it as if the plane was dropping from, you know, a certain height, and you can use pretty simple kinematics equations to find the speed that it picks up at that certain point. And then from there, you just apply, you know, some kind of rough impulse assumption. So I think it was an impulse of like 0.05 or 0.1 seconds that
Okay.
you know, landing force is going to apply over, and then you get the 4 Gs from there.
Okay. So inherently, you're assuming something about the compliance of your airframe structure as you're doing that, right? Like your landing gear is going to compress, and the main gear is going to kind of spread, bow out. Your wings are going to droop a little bit, and so you're going to absorb that kinetic energy as you come down, and it's going to take you that long to absorb the kinetic energy, and that's going to that impulse then is what drives the acceleration. Okay, so you said you had the plane instrument, right? It sounded like you had it instrumented for flight.
Yeah, we had a flight controller, with a flight controller, and it included a gyro compass, a LiDAR, and additional capabilities within it. Yes.
Were you taking like acceleration measurements there?
Yes, the FPV camera showed actually the G-forces as the plane was maneuvering as it took off, and we captured the 3.6 or 3.6 Gs that we were able to capture at maximum during the flight. And that's where we got that number
and
from.
Did you calculate, or did you capture a G loading when you touched down?
You know, actually, the touchdown actually didn't work because we have it in the black box, so I can retrieve it from the black box. But I think we lost our transmitter during flights, so we weren't able to capture that during the touchdown. So the video went up to about 80% with the FPV camera showing, and then the last 20% was out. So we weren't able to capture it. But we have it in black box that I can recover. I'd
be really interested to see how that compares to the G loading you assume for the structural analysis here, and I would suggest that might be the G load that controls the analysis of the wing as well. Let's see, but you know, overall, I think the structural analysis, you did a good job. I like seeing hand calcs here. I like not seeing FEMs here. I like seeing buckling analysis here. So good job on all of that. The actual manufacturing, you mentioned the layup for the main landing gear was like a 45 ply and then 290 plies and then a ply of fiberglass.
Correct.
Was this unidirectional tape or this fabric?
The fiberglass?
Yeah, no, the carbon. I mean, the fiberglass. I have questions about the fiberglass too, but is the carbon tape or fabric?
Okay, so the first, it was a 3K weave, and we put it on a diagonal to change the orientation of the ply, and then the outside, it was laying up on the inside. It's a bit difficult to explain over the video. I hope you can see it okay. But we had one piece on the interior, another piece on the exterior, and then one piece of 90 degree ply that actually wrapped around the whole landing gear as a whole. But that was done.
Oh,
at
okay. So the 90
piece.
ply is sort of both surfaces of it?
Yes, yes. So there's
Okay.
45 on the interior, 90 on the exterior, and then it started on the interior and wrapped around.
Okay. How'd you arrive at that for your layup?
It was estimated that because you can see this white piece on the internal here. That is actually just lightweight PLA, and that's about 3 millimeters, and it was estimated that each layer of carbon fiber that we added was going to be about 1 millimeter in thickness, to get us to that range of like 6 to 8 millimeters in total thickness, as I explained on the other slide. And then as we wrapped it, we had extra carbon fiber at the ends that we kept going around to make the rear landing gear tapered down to 1 inch to make it thicker at the bottom as a little thinner at the top.
Okay. So I mean, what I'm asking is why the specific, sounds like a 90, 45, 45, 90, why that specific layup as opposed to like all 90-degree plies or something else?
Honestly, I feel like I don't have the best.
So we just kind of wanted to support the 45 fiber direction if we had only 090s.
And what we had available as well.
Yes, it was what we had available. That is another addition to the statement.
That is always key. No, I like the answer of supporting the 45s, right? So giving yourself, in the industry we might refer to this as black aluminum, where you kind of lay up in that pattern where you've got sort of an equal number of plies in a plus minus 45 degree and a 090 degree direction, and now you've got sort of a quasi isotropic behavior, which is nice and easy to analyze and behaves predictably. You don't get weird like curing effects. So that, I think you were doing room temperature cure, so that's probably not a major issue. But I wonder if you could have done something to tailor that a little bit more, maybe add a little bit of compliance there, because I know you've got a shock absorber in the nose, and we're kind of tuning the well, I guess you maybe have some opportunity to tune the main landing gear to reduce those hard landing loads, right? I mean, carbon fiber gives you a lot of opportunity to do things where you maintain strength, but also can tune stiffness and control things like impulse loads. So that's maybe something to consider going forward as a future iteration on this if you take it any further. And then the last thing I'll ask is, you talked a little bit about the main landing gear attachment to the fuselage. I don't know that we talked about the attachment of the main gear.
The nose gear or the main gear? I apologize.
I'm sorry, we talked about the nose gear attachment. I don't think we talked about the main gear.
Sure. So it's a bit difficult to see from these images here. In the R1 over here, and we can jump back to the CAD of the fuselage that explains it a bit better. But there is a bracket that's been 3D printed into the fuselage, and it has the landing gear itself has rubber O-rings on. There's one on each side of just inside that fastener, and those O-rings fit into little slots that were made in order to prevent any torsion on the rear landing gear.
I think just to clarify a little bit, these fasteners that you see here, they are just through holes, and there's nuts on the inside of the fuselage for those.
Okay, so it's just kind of sandwiched between like fuselage acreage and that little cover plate underneath?
Correct. And the idea of the cover plate was to provide compression on the O-rings so that the fuselage isn't actually making any contact with the landing gear, and the landing gear could have some spring in that location, and that would reduce the stress on the fuselage.
Yeah, as a like from a load path perspective, I guess you're sort of picking up load into the stringers in the fuselage, but I think I would prefer to see that. Yeah, actually maybe not, because those stringers are further out. I think I'd prefer to see that landing gear kind of centered under one of the ribs, which, is the joint in the fuselage, just so that that vertical load has a place to go that's not like sort of punching through the lower skin of the fuselage.
We did add this little support bracket on both sides that connects it directly to the.
Oh, is that? Oh, okay. Yeah, I see that now. Okay.
That also includes that, and the main reason we wanted to keep it to one side is just to isolate all those design things to one section.
Yeah.
And 3D prints for those.
Okay. Yeah, I guess I see that. What concerns me about that particular arrangement, right, is you're sort of punching into your stringer, and there's not really a good load path to react that. Like punching into the frame is a better solution than punching into the stringer like that. But clearly it worked, right? I mean, you guys were able to successfully land, and it didn't seem like that was a weak part of your design. So
honestly, I think in the future iterations, something that we could do there is add another one of these like mini frames, kind of around that back area there.
yeah, that might be the right way to go there.
Thank you.
Yep, that's all I got.
Yeah, thank you, Tom. So since people are waiting outside, I will do very quick. Is there any other
I
audience?
don't believe there's any
Okay.
questions.
So I will do very quick, since people are waiting outside. So I want to say overall, really great presentation. The slides is very comfortable read. This kind of slide that I really want. It's like every time students have said some templates that I don't have because in the previous semester I didn't really have something like I really like. But this one I probably can use for the future semester. Yeah. Because this is exactly something I really like. It's really focused on the communication part, and not like showing all like even in this final presentation we still have some group like full sentence crowded words on the slide. So I really like this one. And also I think the logic of this whole thing is very clear. And also I feel like everyone's presentation skill improved. Well, it was good last time, but it improved compared with midterm presentation. I can actually feel that you guys are trying to communicate with the audience instead of like try to memorize something you wrote before or anything. You are trying to explain your things to the audience and try to communicate with the audience. That's the feeling I want to see in the presentation. So some small details. I forgot my glasses today. But I think it would be better if you have page number in black. Right now,
White.
yeah, it was not a problem when I was sitting in front of the computer, but I can see everything else. It's just the page number I cannot see. But if it's black, it's like some color with strong contrast. It'd be better for someone like me. And also for small details on page 9. So some very small details. I would prefer you put something like a what x-axis like angle attack or lift coefficient or lift drag ratio on the y-axis.
Yeah.
And also, I mean, you have different color lines. I mean, what each color lines represent what L-foil. You put something there.
Yeah,
Otherwise,
right.
what the point to give the information? I cannot read anything from that graph, right? So this is that one. Page 10. I'm not quite sure what I guess green line is a lift distribution, what the yellow line and red line represent.
The yellow lines represent drag and the red lines represent the downwash.
Okay, you didn't explain in the presentation.
Yeah.
So it's like if you show some information, it's better you explain it. Otherwise, it's like
Okay.
you leave the audience confused, like why you show. Otherwise, you don't show the yellow line or red line. Then I'm fine.
Right.
Yeah. At page 11. So what I'm thinking is that first, for the 3 spars, probably so is it, I mean, it's strong enough, it's already approved, but my question is it necessary to have 3?
So that does go back to Mr. Singer's optimization point. A lot of what we have here is remnants of what we started designing for, what we started manufacturing for, and eventually we did change. So for example, I think in the midterm presentation, we talked about the LAN cable that we were gonna run through the entirety of the wing, and now we're running our wiring throughout the ribs. So this one would be able to be chopped off. Going back to Mr. Stringer's comment, Mr. Singer's comments about aerospace structures. Mr. Singer's comments
I'm
about
okay with Mr. Stringer.
That would be a great professor name. So a lot of what the margin of safety of 6 that goes back to. For that loading condition, a good amount of that is constrained from the fact that we did have to increase the geometry because we were using lightweight PLA.
Okay.
So we tried going one single layer and also the size of the wing itself.
Yeah.
So I think this one we could definitely just get rid of and make that a regular spar. This one was very useful for our layout process, so
Okay.
I think that in either the midterm presentation or this one
Okay.
in the manufacturing slides, we were able to have that hanging down like a coat hanger.
Oh, okay, okay,
And
okay. So it's
ultimately-
not purely for like calculating normal strength of bending, or so it's also for the manufacturer.
No, the back, the most trailing edge one, the most leading edge one, those were the ones that the actual spars were in for.
Okay, okay.
And the middle one was just for electronics.
And we also
Okay.
use them for shear joints as well
Okay.
to glue it.
Okay, now I understand, because my next question, my follow-up question is that if the spar is really for, wait a second, for like carry the normal strength called bending, I would prefer not to the neutral surface, because to the neutral surface, it's carry nothing. If you remember from the mechanics materials, neutral surface, the normal strength caused by bending is 0. So if you have other purpose like electronics, manufacturing, or anything, explained very clearly in the report. If it's for stress, show me the calculation to prove it's necessary.
There was one other thing that it came in very useful during the layout process. To maintain the airfoil form, the middle section, the additional section helped a lot to maintain that airfoil. as
Yeah,
well.
this the middle one, we can eliminate the two that we have here. But definitely it would be, we would need it for the actual integrity of the surface, and
Because
that
the
was
light
another
peeling
one
was
that,
everything.
yeah, that was another element that geometrically increased our decreased the actual stress just because of this bar helping with bending. And like I mentioned, ultimately, without knowing it, and without knowing it, when we took a tumble
Sorry.
going onto the wing itself, it definitely did help a lot. And not just having, because one of our concerns was having the weak rib, it helped carry the stress.
There's not actually a carbon fiber spar in the interior fold.
Okay.
It's just a PLA spar.
Okay,
Mm.
cool. Okay, so, great. Page 12? I don't know.
I think it's the next one.
Yeah, next one.
Yeah, I think when you guys explain this one, you said, oh, okay, it's there. It's minimize dihedral. I think when you guys explain this one, you said minimize dihedral for decrease the bending moment.
Yeah, so in the textbook, it pointed out that one of the issues with having winglets that were pointing up was that then you would have some lift component that was actually pushing the wing into the fuselage. So it did provide not a hugely significant, but some contribution to the moment going inwards. That is what we're referring to, the dihedral of the winglet itself.
So you mean you have that dihedral of the wingtip to decrease the bending moment of the whole wing? Is that what I mean, or decrease?
At the root. So in
It's
the
just this
textbook, it was talking, or
Not that it's going to decrease the bending moment overall, but by not having it be
would-
so great, it's a lower bending moment. Like if it was higher, then it would make more of a bending moment, but here it has less of a.
Oh, okay,
It's still
okay.
going to add.
It's like compare if you have like.
It's still going to add
Yeah.
some
Oh, okay,
bending
okay.
moment, but
Correct.
not as much as if it was
Yeah.
fully up.
Yeah, thank you for the explanation, because I was thinking like, why
Yeah.
actually can decrease the bending moment?
yeah, not decrease, but like Marley said, decrease relative to other designs.
Okay.
Probably change the nature of the wording.
And there are several places you guys talk about torsional rows somewhere. It's like I think it's.
Torsion rod for the.
Sure, it's.
Is there really like torsion rows for those rods?
That's
No, it's a regular.
See,
Yeah, it's a regular hinge.
that's what I want to say. There's no torsional force in that rods. It's like they have their function, but this, yeah, that's what I mean. And a structure analysis for the wingtip. I cannot see the page, but structure analysis, the first structure analysis is for the wing something.
This
Like,
one.
yeah, this one. Yeah, so I probably talked to you too late. I said it's better to
Yeah.
put more information there, but it's like too late. So, so normally when that's why maybe Tom also like was a little confused about this part, because if you put more information, then we can be better, like. And also for this one, I mean, as engineers, we cannot do like for handicap, we cannot do exact like what is the stress there. We do approximation, and it is okay that if you think like have weight at the tip, and then you have same factor 5, you said that is part of a consideration of the load factor or something. I consider that's okay, but we as engineer always want to have some calculation that closer to the reality, right? And something closer to reality is elliptical distribution. And in your graph, the green line, you already showed me that your elliptical distribution.
Yeah.
I mean, if you already have the elliptical distribution, why don't you just use that elliptical distribution instead of using like half weight, right? Let's say in my, because we're different class, if we have this project and some students use elliptical distribution, some students use half weight to the wing tip. I would say, I know this is more conservative, I know, but for aerospace program design, we always want to optimize. I would say the students who use the elliptical distribution, I would give a higher grade. This one is not wrong, but you know
Yeah,
what?
no, I think that's a very fair point. These are also carried over from our initial calculations, because that is a lot of what we focused on where we started placing the ribs. So these are carried over, but I think that you have a very fair point, and that would be a better analysis, and that could also probably help us create a more optimal structure, especially towards the tips of the wing where we don't have as much loading.
Okay, so
Yeah.
Thank you.
landing gear structure analysis.
Look for lots of blue.
Yeah.
It's okay, they can wait. Yeah, they can wait outside, it's okay. So for this one, my feeling is that your design criteria is the deflection, 3 millimeter and some 2.5 millimeter.
So for the rear gear, it was deflection, because obviously that's the most important metric in terms of protecting our camera and
Okay,
when we obviously
that's okay.
install that. But
So
for the front gear, it was deflection was not in the design criteria at all.
okay, so it's okay.
That was just a, hey, this is what it was, just because obviously, you know, you should.
But it's also stress is criteria for your design.
Stress was the criteria for the margin of safety.
Okay,
yes.
okay, that's good. And one thing I want to say that because when you use that maximum deflection, it's assuming that your structure is like is in this direction. You know what I mean? It's like
So
the equation is for cantilever beam,
yeah,
and the force is applying this way. Now your actual landing gear is in this way, and the force applied this way. So
we
there should be some difference.
so we did approximate it as a 45-degree angle beam, but again, you know, your point still stands in terms of like it would be
Is still that equation? I don't think so. The
well,
equation is applied for this one.
well, no, you'd have a 45-degree beam and then it's mounted here. So like if you kind of just rotate it, it's still a cantilever beam. Do you see what I'm saying?
Your boundary condition is here. Your beam like this.
Yeah, so
Your
it
force applied here. You know what I mean?
yeah, so it's not a directly vertical force, it's the component of the landing force that is perpendicular to the beam. So we did approximate, I know it's like a rounded structure. We approximated it as like a beam just from the attachment
beam like
point at the
this.
fuselage
As beam
to
like
the attachment point at the wheel. No,
Like
here, let me.
approximated as an
Explain.
angle.
So a beam attached here to here,
Oh, so it's
and it
this way.
cantilevers from here, yeah,
Okay,
that's
okay.
really,
Okay.
like, I know it's not, you know, like a direct wall, but it
Yeah.
effectively is pretty close to a cantilever beam.
Okay, so it's basically you simulate like this.
Yes,
Yeah.
yeah,
Right.
exactly.
And then you.
And then
What
so
force?
the landing force goes, yeah, obviously vertical, but then you can take the
Okay,
you can take the components, yeah, parallel to the beam and then perpendicular to the beam and
okay,
then.
great job.
A lot
Once
of
then
a lot of these also come, I think you have a good point that it would be better as well for us to take into other presentations, that we go back and do structural analysis with our final designs. Cause I think that we're seeing your points of these are carried over from how we initially started
Yeah.
our sizing, but it would be better to
Yeah.
include more accurate loading conditions to what we actually experienced.
Yeah, I think the explanation is good, and because that part was not included in the presentation, so I'm just curious, like, because the equation itself, when I see it, it's like, it's beautiful.
Yeah,
equation.
Totally
So,
understand.
thanks for the,
I-
clarification.
I
And
would kind of agree with Ting and say like a free body diagram just to show what you were looking at
Yeah.
and the direction of the roads would have helped here. The other thing I'll ask, and you know, looking back at this after we talked about the landing gear, kind of refreshes my memory. What did you guys use for E when you were calculating deflection?
Like modulus?
Yeah.
Yeah.
Oh,
Fiber.
I just used, you know, a pretty general carbon fiber modulus. I think it was 200 GPa was on the lower
Okay.
end.
So what you'll find when, you know, if you wind up doing composite analysis professionally, you'll find that your modulus is going to depend very much on the angle that you lay your fibers up at, right? Like a 90-degree fiber is going to be very weak in compression, and a 0-degree fiber is going to be very stiff in compression, right? So you've got fabric with 0-degree fibers and 90-degree fibers. And then you got fabric with plus minus 45-degree fibers, right? So you've got different stiffnesses of your fiber. You also have different moment of inertia contribution, right? So a 0-degree fiber on the outer surface is going to be more effective in stiffening up against bending than a 0-degree fiber at the neutral axis, right? So that PL cubed over 3EI, that's great for an isotropic material, but when you're looking at composites, things get a little more complicated. So just be aware of that. Not to say that you did a bad job. And again, you know, when you have a 0.45 90 layup where equal fibers in all four of those directions, you can start treating things as isotropic and get back to that type of equation, but your modulus isn't going to be just the modulus of like a 0-degree fiber anymore. It'll be less than that.
Yeah, understood. That makes sense. I think definitely focusing on getting some type of isentropic layup on the landing gear would have been nice. That's a good touch for the future.
Thank you.
Was there any other slide you wish to go to? Was there any other slide that you wish to go
No.
to?
So, one last question. Is this like the one you did test ride, or did you reprint?
That was
That's
the
not
only-
really.
One question, why the other group, it's kind of melted, but your group is fine?
The plastic?
But we were very good about keeping it in the name.
Oh, okay.
Yeah, that was Victor with the.
Me with the umbrella.
Our body was thicker.
Yeah, because the other group, they were like this.
It had very much warps, yes.
Okay.
We kept it in the shade up until it had to go right on.
I think that was also part of their crash that caused that.
No, it's like warped before.
Like some
You can see it a
morphing,
little
I think.
bit in the access hatches.
Yeah.
But it's so much better than the other group.
The wingtips, the winglets are ceremonial black winglets, but we flew with the white ones. And that's because the first ones that broke completely, those have completely deformed because they were painted black.
So, great job.
Thanks so much.
And not just for the presentation, but for the whole semester. And also, I'm just so happy that you guys decided to go to the poster competition. I know you already know that you don't really need that 10 points, but I'm just curious how happy you still decided to go. Since you guys are the only group who have the competition conference, so my feeling that probably you can bring this one to your poster competition tomorrow.
Yeah.
So it'll be super fun. I'll be there tomorrow. So, and I'm very confident that I don't want to stress you guys, but I think you guys gonna win something. Yeah.
No pressure.
Yeah, no pressure.
Can we take a picture of it?
Yeah, of course.
Dr. Ting, will you be in it?
Can we put our plane closer?
Yeah.
No, just,
Yeah, just roll it all the way back there.
I know.
Careful with the computer.
Okay, it's done worse. It's done worse.
Close. It's gonna take a whole bunch. Hold on. Wait, it's still, hold up, wait. Go back to camera. Can you just make sure that?
Yep.
Some of those came out alright, because.
Sure.
Focusing.
Assistance.
Yeah, 6:30, you know what you're saying? Yeah.
Oh, yeah, you moved the knob, really good, so that should be good. It's on. Don't worry. It's totally good,
All better,
alright.
error, yeah. They're all much better, yeah, that's what I was doing.
Yeah.
Last time. Okay. Perfect, hold on, I'm gonna take a bunch. Hold on, a little higher. On the airplane. Yeah. Sorry about that. The other people are really blurry.
That's great. No, that's totally good. Thank you so much.
Yeah.
Awesome.
I would just like to tell you guys, fantastic job. Presentation, also fantastic job. Like, you really, really dove down and like bringing up the issues of like what's wrong. I really like to see that. You identified what's the problem, what's changed, where that was fantastic. A lot of the points were already brought up. And I just want to say, like, at the beginning of the semester, I told you guys this was a class that's gonna make you feel proud. And then all the work and the time that you put in, it should be something great. Well, here it is. You guys should really be proud of yourselves, because the time and the work and the dedication to this item, this product, this airplane, like, fantastic job. Can't
Thank you.
say like how much
Thank you
proud.
so much.
Thanks for you guys, both of you guys as well.
Thank you.
Thanks. You guys are always there.
Detailed shows.
Yes, thank you.
Thank you.
Anyone has a sticker?
Yeah, it's right here. Sorry.
Good job.
Yes.
Thank you guys also on.
Yeah, thank you guys so much.
Thank you. It was a pleasure.
I'll try just provide the details.
Got it.
Right, make way. Yeah.
Thank you, Mr.
Dr. Ting, should I stop the recording and then start it again?
He left.